Hello and welcome to Sean White's Solar and Energy Storage Podcast.
Hello and welcome to Sean Blair White's Solar and Energy Storage Podcast. Yeah, that's right. My middle name is Blair. It's a B, Sean B. White. And I got another B here. It's Blair Reynolds. What's up, Blair Reynolds?
Hey, what's up, Sean Blair? Another episode of Two Blairs, One Cave.
I know, huh?
Yeah.
In one cave. What do cavemen say anyway?
We
right.
we can skip that.
Yeah. No, we're leaving that in. All right. So we were talking not too long ago at RE Plus. We did a couple of podcasts together, actually. One was just both of us, and it was in the podcast booth for 25 minutes, and we were just getting acquainted and talking about PV and some other things. And we decided that we would do some more podcasting. And one of the podcasts actually came up even a little bit later. I had a podcast on the podcast stage with Greg Smith, and then you and Emmett Muckles rushed the stage, man. What's that all about? We had stage rushing.
You need some tighter security, man. That's all I can tell you.
So if anybody hasn't checked that out, it was a lot of fun, and check it out. We'll have it in the link in the show notes. It's on YouTube. It's probably gone viral by now, like millions and millions and millions of people probably already seen it, you know. Yeah. And so we were going to talk maybe about grid forming inverters, UL 3741. And so what's up with all of this stuff?
Yeah. So you're taking me back a little bit here in time, back to my days working for SMA America. I was a product manager for SMA America for about 5 years. And I started off managing the residential product line, which was the Sunny Boy, very famous product.
Back then, too, was that when SMA was the number one inverter in the world, I guess?
Probably not at that point in time. I think this is well after rapid shutdown had come into effect in the US, and we were sort of still dealing with some of the reverberations of that. But no doubt it was, SMA still makes a heck of a product. And just as a company, it's a place you can work and gain like a PhD level, knowledge just from osmosis of, the talent that works there. So
it comes osmosis. Does it come through your skin?
Yeah, I think it does actually. Yeah, I think it does. So look, I graduated my way up into the utility side of the business, supporting their large scale energy storage inverter platforms, including their both AC and DC coupling product strategies and their synchronous grid forming technology, which is actually just software, but it's some of the coolest, most impressive software you've ever heard of.
Cool. So grid forming. Don't we already have a grid? What do we need to form another one for?
Yeah, I mean, it's not a bad question. So, basically, when you go way back in time, some of the very first PV systems were actually truly off-grid, integrated with batteries. And so those inverters at that time were actually grid-forming inverters because they were synthesizing that sine wave or something, a close representation of it, and creating AC power, right? Now, you fast forward to, in time, and grid-tied inverters became really the mainstream thing, which is where you're synchronizing to the grid and you're operating the inverter in a current mode rather than a voltage source mode. So in a current source mode, the inverter is watching the AC grid waveform and is latching onto it, and then it's just pushing current into the grid at that same frequency and that same oscillation.
So it's kind of doing all it can do based on the sunlight.
Yeah, right. Exactly. It's instantaneous power right back onto the grid. Okay, grid-tied inverters. And, for most of the last 2 decades, that's mostly what we've been deploying out there are grid-tied inverters with, coupled to solar, wind, and battery storage systems, right? And so, this idea of having a grid-forming inverter connected to the grid sort of came about as a result of so much of the work that we had done helping deploy renewables out there, that they were actually starting to see that in certain areas on the grid, so much renewable had been deployed that it was actually weakening the strength of the overall grid. And the term that we use to kind of help talk about, the overall strength and resiliency of the grid is the inertia, how much inertia exists on the grid. And this concept is a little bit technical, but sort of the best way to explain it, if you can remember back to your high school physics days, inertia is an object in motion wants to stay in motion, right? That's like sort of the classical Newtonian physics definition of inertia. And when we think about how our 20th century grid sort of came about, it was all built around these machines that spin turbines, right? And create that AC waveform, generators, if you will, right? Fossil fuel generators. And so because those machines have their own rotation and a mass that is rotating, they inherently have inertia, okay? And why that's really important is because in the event that there is a failure, one of these generators, these generating facilities catches fire, blows up, whatever, is taken offline somehow, the rest of the machines that are on that network are still spinning and generating that inertia. And if one of those machines were to fail, that motion, that instantaneous motion wants to remain in motion. And basically that inertia, that feature is critically important to maintaining the stability of the electric grid. So when one of these failures does occur, it gives backup systems time to kick in and react and take over. It's amazing just how fast you can experience a frequency dip on a grid, and then losing frequency by more than maybe 1.5 hertz will cause the entire network to collapse. So having a minimum amount of inertia there to sort of catch a fault on the grid and help sustain it just for a brief instance of time, we're talking on the order of 1 second in time, can make all of the difference to ensuring that backup systems can kick in and take over and maintain stability of the grid. And a great example where we saw this breakdown happen in recent times was out on the Iberian Peninsula earlier this year. I think this was back in May. In fact, I should know, I was in Portugal at the time.
Yeah, I was going to say, isn't Iberian just some fancy way of saying Spain and Portugal?
Yeah, Spain and Portugal. And I was there. It was a bright sunny day just outside of Lisbon. We're having a wonderful time, vacationing over there. And then all of a sudden,
Oh, you were there when it happened?
no power. I was there when it happened, and it was nuts, man.
Maybe you caused it. Are you like some kind of spy?
I couldn't have been good luck because it got pretty intense there for a while. Like, you have to imagine, Europe is not used to dealing with power outages. And this one was totally unprecedented, the scale of it. And it happened in the middle of the day too, which was such an unusual thing. But it was a result of a number of factors, but one of those being at that particular time when this fault occurred on the grid, there was low inertia. And that was in part because there were so many grid-tied inverters, solar inverters in Spain.
Grid-following inverters, too.
Grid
to be
following
more
inverters,
specific.
exactly.
Yeah.
More
Which almost
specifically.
every inverter is these days.
Yeah, but it was, these inverters were not helping to strengthen the network necessarily. They were just latching on to an existing waveform and following it.
Yeah, and one way of looking at it, too, is a lot of people might know about the term anti-islanding. And that's sort of the opposite of grid forming. And when the grid is not working properly, the interactive inverters, the grid-tie inverters, have to turn off.
That's exactly right. Yeah,
To a certain degree. Yeah.
that's exactly right. So this technology that I was responsible for at SMA, this grid forming, synchronous grid forming technology, which, as I mentioned, was literally just software. But what we did was we would overlay this software control on top of an existing inverters. And these were typically energy storage inverters because they need basically always to have some capacity to deliver into the grid in order to do their job and protect the network when there is a fault.
Yeah, and then a reason that the solar inverter can't do that is because it's always working at its peak. And you know what I've thought of, though, is if a solar inverter was made to not work at its peak, it could offer those services, or say if it was clipping or just not putting out as much as it could, then it could always like give you a little extra impulse.
Yeah, or just feed reactive power in to help clean up the grid as well. Yeah, is another interesting way to operate it. But this software control that I was describing, basically what we were doing is we were emulating the physics of that rotating mass. And so we were enabling the inverter to behave, as far as the grid was concerned, it looked just like a traditional fossil fuel generator.
Yeah, I've heard of that called before synthetic inertia.
Synthetic inertia, exactly, or virtual inertia is another term that's used. But that's exactly right. That's what the synchronous grid forming software was designed to do, was provide synthetic inertia. And by emulating the physics of rotating mass, what was so cool about it is we could perform this behavior without any sort of computational measurement and calculation. So there was no feedback loop necessary. It was just inherent in how the inverter operated. And it was so important because you could not have any latency in the time the inverter took over with this injecting synthetic inertia onto the network. And that's so important to maintain because these faults, when they occur, you can lose your grid within milliseconds, and you have to be extremely quick to respond. Inertia helps with that because an object in motion wants to stay in motion. And that's how we were doing it.
Yeah, one thing that I think is kind of amazing too is just with these rotating power plants, the traditional ones, that could be like hydroelectric, nuclear, coal, all these spinning things, is they automatically sync with each other. So you turn on two different plants that are 100 miles away from each other, and they will just automatically sync with each other, which is kind of cool.
That's right.
And so with synthetic inertia, you can do that too.
Exactly. It behaves just like a traditional fossil fuel generator, but we do it with an inverter-based resource. And why that's so important is because it's this technology that enables us to penetrate more than 20 or 30% renewables onto the electric grid. This technology alone enables us to envision a 100% clean energy powered electricity grid.
Some people would say that's blasphemy, the people with the old system.
Well, I'm just saying.
Yeah. No, I'm totally all for that. Yeah.
100%,
110%.
And so by injecting that synthetic inertia onto the grid, you're basically strengthening the grid. You're leaving it in a better place than you found it and bolstering it. And so, without that, traditional grid following inverter-based resources can't connect to weak networks, weak grids. And there was a great example of this, the project that I was involved with in Cape Cod, Massachusetts.
Oh, let's go.
It's like a big arm sticking out into the Atlantic Ocean, right? And so there was a project where we had right here on the very tip of that peninsula. And because the electricity grid ran all the way down from, the mainland Massachusetts, by the time it got all the way out to the tip of the peninsula, the grid was very weak. And it had what we call a low short circuit ratio. So much so that the traditional grid following inverter, it would not be stable connecting to the electricity grid at that point. And so we developed a specialized version of this grid forming control software to deploy at that project site so that we actually strengthened the grid around us and allowed these grid following inverters to then synchronize and connect stably.
You know what I've wondered too is we have synthetic inertia. I'm not 100% sure, but I would think too that perhaps you could improve upon nature of these spinning things and maybe even make something better than the rotating machinery. Like there might be some extra things you could do with like power factor and all that kind of stuff while you're doing the inertia at the same time.
What's so cool about an inverter-based resource is that you can operate it, the waveform, you can generate the waveform however you desire. And so if you want to inject more real power or reactive power, it's totally possible to do that, to play with these variables, because it's essentially a computer deriving this waveform for you. So yeah, it's totally possible. That's what's so cool about a digital grid with inverter-based resources powering it.
Yep. And so another thing too is a lot of times, and even when I first heard about it, when we talk about grid forming inverters, you think of like, oh, the old standalone inverter. And it's not really the case when most people are talking about it. A lot of times when people are talking about grid forming inverters, they're talking about giant multi-megawatt inverters. And so a couple of things I was even thinking, like when you're doing this, do they have smaller grid forming inverters? Like how small do they get? Can you have a grid forming inverter on your house? And another thing is, what would happen if you took a standalone inverter and just connected it to the grid? I wouldn't think it would work. Would there be some way to like hotwire it to make it work?
Yeah, so the application is pretty broad, more than what we were just describing, the whole virtual inertia. And so just, for example, when a power plant does go offline, it is very, very difficult. It takes quite a bit of time, actually, even to get a conventional fossil fuel power plant ramped back up again. And one of the tricks that you can use is actually to use grid forming inverter technology to essentially do what's called a dark start, or sometimes called a black start, to help bring other generators around it back up online by generating initially totally as an off-grid independent system, a waveform that others can synchronize to, other generators can synchronize to. So that is an application. Of course, when you think about off-grid power and, these use cases, this technology also works, but it's completely independent of the electricity grid. You're generating your own microgrid, grid forming inverter for generating a microgrid. But it's that synchronous nature, which is sort of really, I think, the next level of inverter technology, because that's really what helps us get, more and more clean energy out there on the grid stably without creating problems.
So what would happen if somebody took an off-grid inverter and just connected it to the grid?
Yeah, so likely they're going to fight each other, right? The off-grid inverter is not going to know to synchronize to the waveform, so it's going to want to generate its own waveform. And so basically what's going to happen is it'll just be injecting reactive power. It won't be doing anything helpful or useful to the grid at that point. You know, the same way that you wouldn't connect that you're just a standard Honda generator or something like that and try to backfeed it into the electric grid as well, because it's going to want to generate its own waveform at its own pace. And it's going to fight the waveform with the electric grid and basically just giving back reactive power.
So maybe we could look at it as sort of a continuum. And so you have like your total full-on current source inverter, which is like your grid-tied inverter that does anti-islanding, and it's very sensitive and it turns off if not everything's perfect. And then on the other side of the spectrum, you have a total, like grid-forming inverter, which doesn't ever turn off, and it's making the grid. And then you probably have different things in between, and you probably could even set these things differently.
Yeah, that's right. That's right. And I think, really the emerging use case that we're seeing with this technology, this synchronous grid forming technology, is it's basically acting like a giant shock absorber. So when there is a fault or something like that occurs, this inverter-based resource can help support the network for a short period of time, absorbing that shock, while other secondary mechanisms kick in and take over. And that's really the critical role that it's serving in that application.
Okay, and then what are the smallest grid forming inverters that you've worked with? Like, do they get very small? Like, we're not talking about complete standalone, but like one that would be a grid connected grid forming inverter. And I'm sure they probably could make a small one, but there's probably not anybody building 3 kilowatt grid forming inverters, I'd imagine.
The economics today work out better on the larger scale side. So you're typically looking at 2 to 5 megawatt single inverters.
Mm-hmm. And then are these grid forming inverters having to be constantly connected to some grid operator?
They are capable of disconnecting and forming their own microgrid as well. That's another cool feature of this technology.
But is it like the people that are controlling the grid are also controlling these grid forming inverters? Like they're dialing in and like, okay, we need a little more reactive power this minute, or,
Yeah, no, I mean, there is obviously involvement from the grid operators when you're setting up the system, right? And you're going through your operational control plan and approvals and so on and so forth. So they can, grid operators can tell you how they want the settings to be tuned, but these things work autonomously once you turn them on. And that's the whole idea.
So with grid forming inverter technology, what would you say is further ahead, the technology or the policy?
Oh, absolutely the technology. And that's typically how we find ourselves in this industry, right, Sean?
Yeah.
We get ahead of the policy and, oftentimes we find that, we build this technology out of necessity. In this case, it's a necessity that enables us to deploy more solar storage and wind. But yeah, the policy that has been lagging. And thankfully, there are some organizations out there. And if someone was to want to follow up and learn more about this technology, I highly recommend the Energy Systems Integration Group, ESIG.
Just to warm us up, I was listening to their YouTube channel, and I do that a lot. And the problem, though, is they're not as exciting to listen to as we are. They're kind of more engineering type, and we're kind of more fun. I mean, you're a stage rusher, and I'm just a goofball, So.
Yeah. 2 Blairs, yeah.
Yeah, so it's like ESIG, Energy System Engineer Group. And we'll put their link in the show notes. And if anybody out there or knows anybody from that group that wants to be on the podcast, I think it would be kind of cool to talk to some of them. There's a woman that kind of runs it. And I think once, I can't remember her name, but I tried to LinkedIn message her to see if she wanted to be on the podcast, and I couldn't get her on it. So another thing that you were mentioning, though, is like the policy's way behind. And just out of coincidence, I was listening to a podcast this morning, and it's called Freakonomics, speaking of us freaks, and it was called China is Run by Engineers, America is Run by Lawyers. So do you think that helps China's with their grid, like implementing these kind of policies, because we have lawyers like telling us all these reasons why we got to hold back and we can't put this here and there, and they're all suing each other?
Well, there's definitely less red tape in China, right? And less bureaucracy.
Oh, yeah. So are you a communist? Do you think China's better than America? What kind of person
It's
are you?
not what I'm saying. That's not what I'm saying, Sean. I'm saying that what exists in China is an opportunity to deploy technology much quicker at a much scale, and also in some cases with reckless abandon, not
Hmm.
really planning for the consequences. But if it is the will of the local government to help, get a technology out there, it will happen.
I mean, we do know that Shakespeare told us to kill all the lawyers. We just didn't listen.
I don't have any lawyers in my family. I'm not opposed to that plan.
Okay. Most lawyers agree with that. Like if you ask a lawyer, you're like, hey, what do you think about what Shakespeare said about lawyers to kill all the lawyers? And they would be like, that would make the world a better place.
Yeah, they know they suck.
Yeah. Yeah. And they would just do something else, It's like, all right. Well, pretty cool. Yeah. Yeah. So I think that we need to really get the policy to catch up, and we need a combination. I mean, I definitely think we do need more engineers making policy rather than just lawyers like worrying about getting it sued all the time. And there's probably something that each country can learn from the other one.
Yeah, absolutely. Absolutely.
Yep. Freedom. All right. All right. Just that I could even say that. There's probably some place where I would get in trouble just for saying freedom.
We interrupt you for a very important announcement. Sean White's Solar and Energy Storage Podcast has been brought to you by Sean White's Solar and Energy Storage Podcast. That's right, Sean White is sponsoring his own podcast, and he wants to remind you to go check out some of his classes. You can go to SolarSEAN, that's Solar, SEAN.com, and then click on the links to check out his classes. You can check out his heat spring classes, and you can also hire him to teach classes for you, like at your company, something like that. Now back to the show.
So Blair Reynolds, what would I do if I wanted to get a grid forming inverter? Like, what could I do? Would I be able to hook it up?
Well, yeah, I mean, typically you're going to be exposed to grid forming technology in your home battery energy storage products, right?
Well, you just mean like off grid. And I kind of think there's a difference between, like, maybe we should have a better word for it when we talk about like grid forming being like off grid, microgrid, versus grid forming being interacting with the grid.
Yeah, you're right. I mean, it's a good point. Behind the meter application, it really just doesn't make sense at least with the economics today for synchronous grid forming.
What about though, like with virtual power plants? So we have all these energy storage systems, everybody's house and loads and all that kind of stuff. I would think that someday in the future, we're going to have this grid forming technology being like swarm style.
Yeah, it's totally possible. I mean, there's nothing that prevents you from scaling that technology down and putting it in a home battery system. Today when we operate a VPP, we are actually helping the grid, not just because there's a need for more power on the network, but we also boost the voltage, right, when we're injecting power to the grid. So we do help, but not in the same way that, this virtual inertia that I was talking about before. This software tends to be very complex, so therefore very expensive. And so to deploy it it really only makes sense on large projects. And I'm talking like 100 megawatt, 200 megawatt size utility scale projects, energy storage projects.
Cool. Well, how soon until you are going to start seeing this like more common? I don't think that people are doing much of this, especially in the United States. I think in Australia and stuff like that, where there's a huge penetration and a big need for it in lots of rural areas, it's a big thing. But in the United States, I don't think it's a big thing yet.
Well, here's what I'll tell you. My sources on the inside tell me that all of the large utility scale energy storage developers are asking for inverters which are capable of being upgraded with this technology at some point in the future. They know that this will be necessary to deploy at some point in the future on many of their project sites. And therefore, they want to go ahead and plan for it, be prepared for it, so that it can be deployed in as simple as a software upgrade.
Cool. And how much more would it cost to put the hardware in there so you would have that ability?
Well, it's really a software. I mean, the hardware is capable, but it's the software and the controls for the software that enable this type of behavior. And software does not come for free. You invest a lot of money in engineering time and resources and testing and so forth to build good software. So, it is, at least in the current climate, a fairly expensive software upgrade.
So, I mean, could I take any like grid following inverter and just upgrade the software and do grid forming with it?
Yeah, I mean, there are some things necessary to plan for as it relates to fusing and things of this nature, short circuit sizing and cables and all this kind of thing. But yeah, in principle, yes.
Huh. Okay, that's pretty cool. How about could I just take my car and do a software upgrade and then have that be grid forming and then export? Would that be software too? Like, your car goes one way and it goes AC to DC when you plug it in your house. Could that also be a software thing too, to go DC to AC from your car, do you think?
Yeah, I suppose using the inverter that's already built into your vehicle, you mean?
Well, I mean, I guess there's a couple of things. So I'm thinking the charger, could you make the charger work backwards? Probably would need some more hardware or something like that. And then there is the inverter that spins the wheels, and that would give you a whole ton of power to go out there and burn up some wires and send to the grid.
Well, yeah, what you're talking about here, I think, is so when I was working at SunPower, I helped develop a platform for a large US-based automotive manufacturer, which enabled us to interface a large EV battery directly into a home's energy ecosystem. And, so we would install, solar battery storage in a home, but we designed this interface, which was essentially a DC-DC converter that then would connect to the DC port on the vehicle, the fast charging port.
Great.
And so because the vehicle had a battery of something like 400, or I think some cases 800 volts on some of these newer EVs, we would blend the voltage coming from the EV's battery to match the voltage of our battery system, okay? And then we could extract the electrons from either our home battery system or the EV's battery system at will, and use it to power the home, use it to send power back into the grid and V2G applications. And so, yeah, this was some pretty interesting and cutting edge stuff that I got a chance to work on.
Okay, so you've been all over. You were working at SunPower too. Is their bankruptcy your fault?
Probably. I think I'll take the blame over Peter
Yeah,
Pearcy.
that's good for you to not try to hide that.
You know what it was? Is I was trying to force a product roadmap that it moved the company away from AC modules, pure AC modules, and more focused on a product line that was DC coupled energy storage and leveraged the capabilities of the UL 3741 standard.
Gosh, you are kind of got that Forrest Gump thing, being at all these different companies. I know you're at Belis Solar right now, making Made in America PV modules.
That's right.
SMA, SunPower, that's all pretty cool. And so I also know too that I was reading some stuff one time, and SMA came out with this thing, and they were working with Solega and Iron Ridge and Ray Tray and all this stuff. And they came up with this UL 3741 that is really popular right now. It was a little bit controversial too, but you kind of pioneered that. And do you have patents?
Yeah, it's an application in the 3741. Is obviously a UL standard, and the application that we developed at SMA was not really a patentable technology per se. There really wasn't any specific IP involved in that application. But I did develop 2 patents with my team around grid forming technology when I was at SMA.
Oh, wow. That's pretty cool. You must be a billionaire.
Yeah, not quite. I think SMA bought me out of one of those patents. They were going to send me $1. At least I signed a contract saying they were going to send me $1. And I never received the check. I'm actually still pretty upset about that.
Oh, dang.
I really want my $1.
All right. I know you might have invested it in something that went up a lot. So come on, you SMA people, give Blair Reynolds his $1.
I need my $1.
What's up with that? So you've got 2 patents on the grid forming technology. Maybe you could talk a little bit more too about what it was like coming up with that UL 3741. It was the first one that I ever heard of where you could do rapid shutdown and still keep it 1,000 volts inside of the array. I'm pretty sure that was the first one that could do that, and people are still using it right now. And what was it like coming up with that? Were you the main guy behind that?
Yeah, actually, I think I will take credit for this.
So you kind of started a revolution because now everybody's doing it.
Yeah. I saw the opportunity there. And I know that the US installers are constantly looking for ways to remain more competitive and design, higher quality systems. So yeah, that was really the genesis behind it. The idea came out of, we had an internal crowdsourcing competition at SMA called the Kickbox program, the Kickbox competition. And so we would crowdsource, good ideas for the next product or service And so anyone in the company globally could participate. And so I entered the competition one year. I think this was 2020, the COVID year. And turns out I won the competition with this idea for how to
Wow.
come up with.
Congratulations.
Thank you. Thank you. Still waiting for my dollar on that one too.
Uh-huh.
Came up with this idea for how we could leverage a standard that was getting ready to come out, getting ready to be published by UL, the 3741 standard, and leverage it in a way where we could design fully code compliant systems and use the inverter as the rapid shutdown device rather than module level power electronics. And I thought this would be so important because module level power electronics, while they do a lot of great things, they also add a lot of complexity to the system. They certainly add cost to the system. And unfortunately, they have been shown to add reliability problems to the system as well, particularly when you look at the number of physical connectors that are involved with installing MLPEs on a rooftop.
And before too, like, so the 2017 and the 2014 NEC up until 2019 let you do what we would call array level shutdown instead of like UL 3741. And so people were still doing that with like the inverters, I guess. Yeah, using the
it was possible back
anti-islanding.
then. Yeah, that was the 2014 code cycle. And then in 2017 code, we got the opportunity to start, well, we sunset that array level shutdown strategy. And there was a deadline in the code, I think it was January 1st, 2019, where
Correct.
we had to obey by 690.12b2, which
Correct.
created a separation of controlling the conductors both inside and outside the array boundary.
Yeah, yep, you got it. Yeah, and then I remember I actually did a podcast on reading that. Like when I first saw that you had like full voltage after shutdown up to 1,000 volts. When that came out, I was going, wow, check this out. And I did a whole podcast on it. We'll put it in the show notes. And when was that? It was like, I'm trying to think of what year that came out.
Yeah, so we started to see the first certification roll out around in the early 2022 timeframe.
Yeah.
So the standard wasn't published until 2020.
Yeah, I think it was December 2020.
December 2020. And so once that standard was published, we now had a framework that we could go out and test to. And so what the standard was, it was all about how to design through an FMEA, a failure mode and effects analysis, a way to ensure that firefighters interacting with a PV array would be safe and create an actual system level certification for products that had been tested in unique combination with each other to ensure that this was possible and that firefighters would be safe interacting with that array under a variety of scenarios. So basically, what can happen on a roof that could injure a firefighter? Things like a trip and fall incident, a firefighter slipping and falling with a tool in their belt, like an axe, for example, and what if that axe penetrated the glass on a PV module? So they went through all these different potential scenarios, came up with the test plans for each one of these scenarios, and then we would conduct empirical testing on the 3741 standard to ensure that the combination of equipment, when installed a certain way on a roof, was inherently safe and proven to be safe through empirical testing. And so, I think it's a common misconception around rapid shutdown in our industry. I think if you go back and you ask the old timers, what was really the intent of 690.12 rapid shutdown, it was not about reducing the likelihood of a fire. 690.12 was all about protecting firefighters. That was the intent
it
behind it all.
specifically says it in the code now, just firefighters.
Fire protection, exactly. And so I think some companies had latched onto this notion and created this idea that module level power electronics would make it less likely for a PV system to have a thermal event. But looking back at the data over time, that has not been the case. There has been no significant reduction in the amount of fires that we see in rooftop PV systems. In fact, we have seen that trending upwards. And oftentimes it's pointed to issues with connectors, mismated connectors, or not poorly formed connections on the roof, because DC is tricky to deal with. And so what I realized in the 3741 standard is that it really created an opportunity for us as an industry to put a lot more focus and emphasis on wire management, because wire management is so critical to the longevity, performance of the PV system. And really, as you know, is kind of what separates the best in class installers out there from the newbies, from the rookies. And, we can harp on it all we want, but when the standard presented this opportunity for us to, engineer a better way to manage cable and to ensure that process was repeatable, and to ensure that that was going to add to the longevity of the system and not create additional safety risk, I said, this is the right time to do it. And not only will it help us engineer out these extra devices, the extra cost and reliability problems, lifetime service risk that come with having to replace MLPEs over time on the roof, it's just going to make us better as an industry by putting more focus and emphasis on the cable management.
Cool, cool. Do you know who Solar Boy is?
Oh, yeah, Derek. Yeah.
Yeah, Derek Mast. He has a website called ul3741.com, and it's pretty much based on like listing all the different products that did what you developed with that first one that came out with SMA there. So.
Yeah, it's been cool to see. Like, I feel like I've passed the torch on to others and they're taking it and running with it. I mean, but this first project that we did, you mentioned Saliga and, they had the sort of the plastic bucket. We looked at that mounting system first because, it had simply just less metal than others. And we thought that that was going to be a good thing for improving the safety of the PD array for firefighters to interact with. I mean, it's sort of a critical concept that came out of the 3741 standard development is that, a firefighter is not at risk if they're putting themselves in the path of live current. For a firefighter to be at risk of injury from electricity, they have to be in the path of current and the path to ground, right? And so the more metal and particularly the more grounded metal you have on the roof, therefore the more likely or more opportunity to be in contact with the path to ground. So we originally looked at the Saliga stuff, but we didn't really know at that time if we would be able to pass all the tests and still maintain 1,000 volts inside the array boundary and allow the inverter to effectively be this array level rapid shutdown device. So that was sort of one of the fun and interesting things that came out of that first project was he said, we actually proved it was possible to build safe 1,000 volt systems that were unwrapped in a shutdown mode.
Great. Well, that's pretty awesome. So you've been there for a lot of stuff. What's next?
For me or for the industry?
Yeah, well, like for you, yeah, because you're kind of like doing that Forrest Gump thing. And so you got like the UL3741. You're pretty much the first one to do that. You were like doing grid forming technology, getting patents and stuff for that. And now you're like doing this Made in America solar thing.
Yeah. Well, I'll tell you what, I'll give you a little hint. So obviously America's playing catch up right now to China on the technology front. We're still deploying a lot of PERC technology here in the US, whereas most of the world is deploying TOPCon technology in solar. But China has moved on from TOPCon. The top 3 manufacturers in China now are all building high efficiency back contact types of solar cells into their product lines. And so what I see here in the US is an opportunity for America to sort of leapfrog and get ahead of some of the largest manufacturers in China in terms of that efficiency and technology curve. And there is an opportunity to do that with emerging solar cell technologies, particularly tandem solar cell technologies. So I had a really fun project that I worked on when I was also at SunPower. We collaborated with First Solar. You might know them, most well-known thin film manufacturer in the world, CadTel module.
For sure.
We partnered with First Solar to develop a prototype of a tandem PV module which had a much, much higher efficiency than either a standard First Solar module or a standard mono PERC technology module. So what we did was we embedded solar cells, your standard silicon solar cells, in the same encapsulant, but underneath a layer of glass that had the First Solar CadTel semiconductor deposited onto it. And so essentially what we did was we stacked 2 solar modules on top of each other in the same encapsulant, in the same frame, and we had those modules connected then in parallel inside the module junction box and created what's called a 4-terminal tandem module. So basically the thin film captured about 80% of the light, but allowed another 20% to pass through and be collected down on the bottom layer, which was the regular silicon solar cell layer. And so what that did was it gave like just an extra boost of power and efficiency to the output of the module, putting it on a path to be well over 25% efficiency. And so, yeah, it was a really cool project to be a part of. And we demonstrated that it's totally possible to do it like this and, leverage the stacking of solar cells on top of each other in the same product to increase your efficiency. And you can even tune one layer of the solar cell to a specific wavelength of light and tune the other solar cell layer to a different wavelength of light and help optimize them further that way, which is really where things got interesting and fun.
That's pretty cool. That's like a solar sandwich.
It is. It's totally a solar sandwich.
Yeah, I had somebody on the podcast that developed a solar glass that had thin film in it, and then you put that on top of the cells. Is that what you're talking about?
That's one way of approaching it. I think you're talking about perovskite solar in this case.
Yeah.
But yeah, that is also a really, really interesting field as well. The depositing perovskites, which are like a thin film solar cell technology, either directly onto the glass or onto the surface of the silicon solar cell. Both are possible and have been demonstrated commercially.
Well, you sure are smart, Blair Reynolds. It must be those Blair genes that we have.
Probably the Blair genes. Yeah.
Okay. Well, I think we should do some more talking even after this podcast, if you got the time.
Yeah, Sean.
Do some more podcasting, because it's been great talking to you, learning about all these different things. And then you're also kind of fun, how you rushed the stage. And, we had physical contact while I was trying to stop you and Emmett for rushing Greg's stage up there when he was my guest.
I'm just such a fan of Greg Smith. What can I say? The battery-powered home changed my life. It's just, it's hard to stay away from the guy.
Yep. Well, great. So let's see, any famous last words for this podcast before we call it a day and then do another one at a different time?
Don't believe anything anyone like me ever tells you. Go learn it yourself. And
all right.
Don't follow me on LinkedIn. I don't want to be your friend.
All right. Well, we heard it, and we're going to put that link there anyway, just so you could go there and unfollow Blair. I'll tell you how to unfollow people. All right. Well, thank you so much, Blair Reynolds, and thanks for listening to Sean Blair White's Solar and Energy Storage Podcast. Go get yourself NABCEP certified. Learn all about UL 3741 and grid forming inverters and all of this stuff that Blair Reynolds has all these patents for. And take it easy, man. Good talking to you, Blair.
Thanks, Sean. It's great.
Ow.
Appreciate you.